Right. Hello, everyone. This is Astronomy on Tap coming back to you for another week of astronomy talks. So for those of you who are joining us for the first time, so the format is that we, initially we would meet in a pub, which, we haven't done for now 3 months. And so, you would grab a drink, you would bring some snacks, and, it's very relaxed. So tonight we're going to talk about ghost particles. And for those of you who are coming back, thanks again. Don't forget to subscribe to the channel to get more info on new videos. And tonight I have with me Chiara Cercosta, as usual, who will present our speaker for tonight.
Hi, everyone. Yep, our speaker today is Dr. Arthur Loureiro. He's a postdoc working both at UCL and Imperial College, and his talk today will be about how to weigh ghost particle, which is a neutrino, by using the whole universe as a scale. So Arthur, your topic today is kind of in between particle physics and cosmology, but you are actually a cosmologist. And yeah, I think cosmology is a very fascinating discipline for the public, for all the studies about the birth and the evolution of the universe. But what brought you to choose this path as a cosmologist?
So, hello, everyone. First, thanks for inviting me and having me and supporting this amazing initiative. So yeah, I think I mentioned when we had a meeting earlier that this was a very funny story. Actually, in high school, I was terrible in maths. All I wanted was to be a bass player. And at some point, I decided maybe I'll try engineering, started liking maths a bit. And I went to a talk by Professor Marcelo Gleiser. So he's a Brazilian cosmologist. And he had just finished a book about the life of Kepler. And I watched that talk and I was fascinated because the life of Johannes Kepler is just full of plot twists and there's actual villains and all that. And I was very excited about it. And I thought you know what, I really want to read this book. So I went to the bookstore and I got the first book that I saw. It was written by Marcelo Gleiser. And I started reading and it was the wrong book. It was a book about the whole history and anthropology of cosmology, from the myths of creation to modern cosmology until what we call the standard model of cosmology is developed. So it was a bit of a mistake that made me fall completely in love by this field that I didn't even know existed before.
Cool. So it was actually the right mistake to do.
Yeah.
Yeah, so just before you start talking about your research, today we posted on our social media a very cool picture with some questions. So let me show you the picture here. Can you see my screen?
Yes.
Yeah. Okay, so this is a picture of the first detection of a neutrino in a hydrogen bubble chamber. And the question is, what is the signature of the neutrino and what are we actually seeing? So I don't give you any more clues. Think about it, and then after Arthur's talk, then we'll give you the answer.
Right. Thank you, Chiara. And again, before we start, we have a little time lag between the feed and YouTube. So you can already start posting questions during the talk. And we will then ask Arthur about, we will ask Arthur all your amazing questions. And I'm sure he'll be very happy to answer. Yes. Okay, cool. So I think that's all I have to say. Yeah, announcement about the next talk will be after the talk, of course, as usual. So I hope you're ready. Otherwise, be ready, get ready, pause, get yourself a drink, and we can have Arthur now presenting. The screen is yours.
Okay. Okay. So is that working?
Yes, amazing.
Great. Okay. So today I prepare this little talk to explain to you how we can weight these ghost particles, or as Chiara already gave a spoiler, what we call neutrinos, using the whole cosmos. So to understand that, first we need to know and understand what are the neutrinos. why do they have a mass and why does that matter? And also, why are they called ghost particles? And how do we actually catch a ghost? So let's start with the standard model of particle physics. This is one of the most reliable theories that we have in physics. It has hundreds of very accurate predictions, and we actually can verify these predictions, and we have verified pretty much all of these predictions with experiments in very advanced labs. So the standard model of particle physics is this theory that explains how most of the forces except the gravitational one in nature work, and what all the fundamental particles of nature actually are. And when we say fundamental particles, what we mean is that these particles cannot be divided into even more elementary particles, right? So everything that we know in our periodic table and even outside of it is built from these elementary particles. One example of these particles that we know quite well is the electron. And the neutrinos are actually from the same family as the electrons. They are called leptons. And the neutrinos come in 3 flavors. And flavors is actually the name that we use to distinguish them. They are called the tau neutrino, the mu neutrino, and the electron neutrino. And this makes neutrinos also one of the most abundant particles in the universe. But why are they called ghost particles? So as the name suggests, neutrinos are neutral particles. They don't have a positive or a negative charge, which means that they don't interact with the electromagnetic field, making them literally invisible to the eye. They also have a very weird property. So all the particles in the standard model have what we call a mirror image. So for example, the electron has a mirror image that is a positive charged electron. It's different from the positron. But the neutrino looks like it doesn't have this mirror image. So all neutrinos are, in a certain sense, left-handed. So I guess that not only neutrinos are the ghosts of nature, they're also the vampires of nature, if they have no mirror image. And finally, what really defines neutrinos as ghost particles is that they are very weakly interactive. They only interact through the weak nuclear force and through the gravitational force. So that means that a neutrino that was generated in the sun can actually travel through 2 light years of pure lead before it hits anything. This is almost half the distance between our sun and the closest solar system to ours, Alpha Centauri. That is 4.3 light years away from us. It is a lot. These guys are really, really, really elusive and non-interactive. To put you into perspective, the radiation from a nuclear fallout can be stopped by only 10 centimeters of lead, right? But should we be worried about the number of neutrinos hitting us? Is this a problem? Do we need to shield ourselves? So for every 10 million billion neutrinos that comes from the sun and passes through the Earth, only 1 of them will interact with us. So let me just move to explain that we do understand very well how the neutrinos are generated, and we understand very well how the neutrinos are generated in the sun. So these types of neutrinos that the sun produces are called the electron neutrinos, and we had very precise calculations in the early 60s of how many electron neutrinos should be produced in our sun. We built these very fancy detectors, and we have now even fancier detectors. And what we notice is that around 1/3 of the neutrinos that should be coming from the sun to our detectors were missing. And that was very weird. We were very confident that our calculations were all correct. And we were very confident that our detectors were working quite well. So the solution came after 30 years of research and building fancier and super beautiful, complex detectors. And the solution is something that we call the Neutrino Oscillations. So the point is that these 3 little guys, the electron neutrino, the tau neutrino, and the mu neutrino, they are what we call the interaction neutrino. So these names come from the interactions that give, let's say, birth to these neutrinos. But when neutrinos are moving, and they move very, very fast, almost close to the speed of light, they have this weird property. So they actually manifest themselves as 3 different types of mass species. And the problem is that there's not a one-to-one correspondence between the interactive neutrinos and their mass species. It's actually a very complicated thing that we call quantum superposition. So as the neutrinos are traveling, they are these quantum superpositions. And when they are detected, they become one of these 3. So explaining in a better way, what happens is that a neutrino electron that was generated in the sun, as it travels through the Earth, can actually change its identity. And when it arrives at us, it could be a moon neutrino. So that's why our detectors were not actually capturing these guys. So just reviewing what this means is that because neutrinos have mass, they then have this weird property of changing their identity. But how do we know they have a mass? So the question is like, who are you going to call to catch a ghost? And it's not the Ghostbusters, it's the Super Kamiokande, for example. So this is a giant water reservoir that we put underground to shield from every other types of cosmic rays and particles that we can see. And we fill it with water, and then we hope that as the neutrinos are passing through the Earth, at least one of them will hit an atom on this water tank. And when a neutrino hits this atom, it creates a shower of particles that will be faster than the speed of light under the water, and will emit this thing that we call the Cherenkov radiation. And this radiation then is detected by these beautiful golden globes that we see here on the wall of the Super Kamiokande in Japan. But the problem when we build detectors is that we can only study the interactive neutrinos because, well, the detectors are interacting with the neutrinos. And that makes it complicated to understand their masses. That's mostly because we only check the differences in masses between these interactive neutrinos. So with these detectors, we can only measure the difference between 2 out of these 3 species. And we don't know if we have 2 very light ones and 1 very heavy neutrino, very heavy, or if we have 1 very light one and 2 more heavier ones, right? And also another thing that we don't know is, well, first, which one is the lightest and how light it is. So with the detectors, we have this problem, right? We can't actually measure the individual masses because once we detect, they're interacting. So we should find another way. We should find something that is sensitive only to the 1 and 2 and 3 species instead of the electron neutrino, moon neutrino, and tau neutrino. So one idea that people had a while ago is that we could maybe reverse engineer the universe. And if we understand well how to describe the universe in a very simple way, maybe we can understand how the masses of neutrinos affect the universe. But first, what do we need to understand how the universe is made? Well, one of the biggest and most important probes that we have to study the universe is called the cosmic microwave background. This is the very first light that our universe emitted after the Big Bang. And by studying these tiny little differences between temperature in the sky, so this radiation is just absolutely everywhere, we can understand a lot about the structure of our universe, the initial conditions of our universe, and also we understand that these tiny deviations into the temperature of this light will become the seeds to larger structures like clusters of galaxies and the galaxies themselves. But this probe alone won't help. We also need to understand the distances in the universe, which are quite complicated. So we have this specific type of supernova called supernova type 1a that explodes in a very easy way to understand brightness. So using the brightness of this explosion over time, we can standardize these supernova and have distance measurements in our universe. But that's also not enough. You also need to add to this the biggest 3D map of galaxies in the universe that we have so far. And that is from a telescope called BOSS, and it has 1.15 million galaxies. And I'm not gonna lie to you, this is not how a 3D map of galaxies looks like, because photos don't actually tell you about the 3rd dimension. We actually have to use a technique that's called spectroscopy. And this is how this is actually how it looks like. So each of these dots that we're seeing on the screen is one little galaxy, right? And this is just a tiny little portion of this data set. So now that we have the very first light of since the Big Bang, thousands of supernova, and the largest 3D map of galaxies, we can summarize this data into a theory that needs only 6 numbers. So by tweaking these 6 dials thousands and thousands of times and comparing the theory that we know very well with the data that we have, we can understand what the universe is made of. The 6 numbers are the age of the universe, the amount of dark matter in the universe, the amount of regular matter in the universe, so the stuff that you and I are made of, and 3 other parameters that are related to the very initial conditions of our universe. And when we do these very fancy type of analysis, what we find is that our universe is 70% almost made of these weird component called dark energy, 27% made out of this even weirder component called dark matter, and only a little bit more than 5% are the stuff that we can describe by that very incredible standard model of particle physics. If you don't remember what dark energy is, it is that weird force that we see in the universe that causes these accelerated expansion in it, so that the galaxies that are furthest away from you will move faster from you than the galaxies that are close by. And dark matter is even weirder, I think, in my opinion, mostly because when we compare the mass of galaxies by the light that they emit with the mass that we know the galaxies should have through their dynamics or how they're moving, it looks like around 80% of the mass that should be there, it's not there. So maybe we have these weird particle that interacts very weakly, probably only gravitationally, and it cannot be seen because it doesn't interact with the electromagnetic field. And if you're thinking now, and I hope you are, wait a second, so are neutrinos just dark matter, or isn't dark matter just neutrinos? The quick answer to that is that no, unfortunately not, and actually it's a blessing that is not, and I'm going to explain to you right now why. So for that, we need to understand how the massive neutrinos actually affect the structure of galaxies and structure of the universe around us. So one of the things that physicists and cosmologists know how to do very well is to use extremely fancy computers to do these very, very expensive simulations of the whole universe. We understand the gravity up to a very good level that we can actually simulate the whole universe. So here I'm showing you just a cross-section of the matter distribution in the universe for a universe without any neutrinos. So if you're looking at this and you're a bit confused of what it is, just imagine that in these little red blobs that you're seeing is where the galaxies would expect to be forming. If we add massive neutrinos, so if we consider that those 1, 2, and 3 neutrinos are massive, what we see is this kind of diffusion effect in the structure of galaxies around us. So what is happening here is that, as I mentioned, the neutrinos, they're very, very fast. They are almost moving at the speed of light. But if they do have mass, what will happen is that they're going to drag away a little bit of that mass through gravitational interaction. So they're very fast, moving around everywhere and dragging a little bit of matter with them. So two conclusions that we have is that, one, our universe seems to be sensitive to how massive the neutrinos are, but how massive the 3 of them are at the same time, like the sum of the 3 masses. And also, if they actually were dark matter, if they were as abundant as dark matter is, galaxies would not be able to form because neutrinos are very, very fast. So if they were very, very massive, they would just carry everything around. The clusters of galaxies wouldn't form and galaxies wouldn't be able to form as well. So they could be, but they are not, and that's a good thing. So now we know that our universe is sensitive to these sum of the 3 masses of the neutrinos. So we can go back to our standard model of cosmology where we have those 6 dials to understand the whole universe. And if we incorporate that information that we know about the differences on the masses that we know from our detectors here on Earth, And the fact that we only don't know the lightest neutrino, we could add the lightest neutrino as one of these 6 parameters and see how well our theory will fit all the data that we have with the supernovas, the first light after the Big Bang, the largest 3D map of galaxies, our neutrino detectors, our neutrino reactors, and thousands of experiments all together. What we find in the end of the day is that around 0.67 of all of the universe is made out of massive neutrinos. And if you think like 0.67 is nothing, like there's 70% of dark energy, we don't know what that is. Just think of the fact that every time you think about the universe, you think about stars. And there's less percent of stars in the universe than there are neutrinos. Stars are just 0.50% of everything that we know. So going back to those questions about the neutrino masses, we still don't know which of them is the lightest. We will need the next generation of supermassive telescopes and space telescopes to, if we have a lot of luck, maybe determine which one of these guys is the lightest. But we do know now, using all of these experiments combined, that the lightest of them is at least 6 million times lighter than the electron. That is very, very light. How light it is? That is 10 to the minus 39 grams. It's almost nothing. So thanks, guys. If you have any questions, you can ask them now or find me on Twitter. And before we go to the questions, I would just like to let these link over here. If you're like me and you couldn't go to the demonstrations today, but you still want to help, this link has a lot of information on how you can help the people fighting on the front of the Black Lives Matter movement. And thank you.
Thank you, Arthur, for sharing all of this, sharing the links. Maybe if you stop your screen or
yeah,
yeah.
Let me do that. And
so yeah, please start asking questions on YouTube. Before we show the answer to the questions Chiara asked, I have to say, if you put these neutrinos on a T-shirt, I will buy it. It's the cutest neutrinos I've ever seen. I think it should be mandatory that all textbooks have ghost neutrino. I mean, they're just so cute. Really, there is a.
Yeah, I spent hours just making them. I was so happy they looked so cute. They're very indifferent. And they have this very indifferent face, like I actually imagine neutrinos being extremely indifferent to everything.
That's a good that's a good analogy. So yeah, before questions, Chiara, perhaps the answer to the questions.
Yeah, sure. Can you see my screen?
Yes.
Perfect. Okay, so this again is the picture I showed you before, and here you have the answer. So here we have labels showing us the spot where the neutrino collides, because we cannot track the neutrino. We can see the spot where the neutrino interacts with a proton here. And then the result of this interaction is that there are 2 mesons formed. This is actually the first detection of a neutrino in 1970, and maybe Arthur, you can comment a bit on the reaction going on here.
Yeah, so the neutrino was actually, so I think it's a very fun story of how we found out that there should be such a particle called the neutrino. So I think it was Pauli that, just using simple conservation of momentum, realized that because of the way the particles are going when there is a beta decay, there should be an invisible, very weakly interactive particle that should go all the way opposite to the particles where they were being let out due to beta decay. And it was Enrico Fermi, an Italian physicist, that said, like, there should be a tiny little neutron, and that, Chiara can correct me if I'm wrong, it's a neutrino. So they predicted that, and it took a few years to actually build the experiment and to be able to see it. And we're still building these kind of experiments. They're incredible experiments that are having some good and bad press in the media. I think a lot of people saw about the ANITA experiment, that is a neutrino detector in a balloon in the Antarctica last week, that did not detect time reversed universe.
So just a question from me, Arthur, is, so we have most particles in the standard model. Correct me if I'm wrong. I'm not at all a particle physicist. Am I incorrect in saying that the neutrino is the only one we don't know the mass of, now that we have the Higgs boson? And I mean, it's the only one missing, right?
Yeah, so the neutrino, so if you do, I was actually on a very funny afternoon, this is not sarcasm, where we're doing these study group about particle physics, and one of the postdocs in UCL, Stephen, was explaining the Higgs mechanism. And one of the funny consequences when you introduce the Higgs mechanism to explain why particles have mass is that the neutrinos don't. For you to have massive neutrinos, you have to add stuff to the standard model. So there are at least 3 ways that you can try to explain why neutrinos have mass. One of them is that if neutrinos, if their mirror image is actually their own image, so if the anti-neutrino is the neutrino, that could explain why they have a mass, but we still don't know. It's still something that is beyond the standard model of particle physics.
Arthur, so what are the kind of future developments in terms of data, for example, that cosmologists are planning to, help understand a bit this problem?
So from the particle physics point of view, there are amazing experiments like Dune, or and I think one that's worth mentioning, there's the SNO, but one that's worth mentioning is called Catherine. So this is an experiment that is actually trying to measure the mass of neutrinos from the point of view of particle physics. What people on Catherine or people in particle physics don't like much is that it seems like using cosmology, we are a bit more sensitive to these masses than Catherine is. So I think the future could be by, and I'm a big advocate of this, of joining forces. So joining the things that we know from the particle physics experiments with the things that we know from cosmology. So there are several new large and space telescopes that are planned for the future. It's worth mentioning also the current telescopes. So we have currently the Dark Energy Survey. There's also the Kilodegree Survey. These are photometric telescopes, so they take photos. So we don't have actually a 3D map. In the 3D side of things, we have the Dark Energy Spectroscopic Instrument, or DESI, where like one of the parts of the instrument was actually built in the basement in UCL. And I think if you combine all these experiments, and we have in the future the Rubin Observatory coming, and we also have the Euclid Space Telescope, and these experiments will observe millions and billions of galaxies, some of them millions, and telescopes like Euclid billions of galaxies. And the more galaxies you have, the better data you have to understand, because neutrinos are very tricky, and the way they affect the universe is also very, very tricky, is in the very, very small scales. So the more powerful your telescope is, the better you can understand this part where the neutrinos affect.
So Arthur, you've talked a lot there about the astronomical side. We have a question here about, I think, more on-the-ground experiments. So can you describe? So you've shown Kamiokande. Are there any other experiments? Where are they? What do they look like?
Yes, so there's one that is, I think it's fascinating. It's called IceCube. So because, as I mentioned, like, it's easy to detect them when neutrinos go through like very, very pure water, and the purest water in the planet is in the poles. So IceCube is a telescope in the South Pole, if I'm not mistaken, like in the in the ice, and they dig miles and miles of detectors into the pure ice, and they have this large facility over there. So if a neutrino that is passing through the Earth hits one of the molecules in the one of the atoms in the ice, it will create that glow. But these glows and these events are so rare that apparently they actually give names to the neutrinos. Like they give weird names to them. They can name each individual neutrino. There are other Kamiokande-like experiments. There's really a lot of them. They are getting very, very, very expensive and fancy, but it used to be easy to build these detectors. So like these detectors in the 60s, they were made with these cleaning product like chloride or something, and as the neutrino would hit, then it would create an element of argon. So you could just check how much argon you have, and you could you knew that that argon can only be produced by a neutrino heating the cleaning product. I hope that answered.
Yeah, no, that's great answer. It's fascinating. Yeah, Chiara, you were.
Yeah, maybe you can describe maybe in your like daily research if you work mainly on data or on simulations or both.
Yeah, so I think the daily work for a cosmologist is way less fun than people think, right? It is, let's say, 90 days of sitting down and thinking, why doesn't my code work? Or what is going on? A lot of error estimation. There is something very peculiar about the universe is that there's only one. So if you want to estimate your errors, and let's say you are a particle physicist and you have a machine, so you just run your machine several times and you have lots of data. But there's only one universe. So if you want to understand the errors in your experiment, you have to model and simulate it very, very well. And this is very important. So most of the days is simulating the universe, checking if it looks like the data you have, and if it doesn't, you do it again. And then you check if it makes sense, and then it doesn't, and you do it again, and then one day you have results and they don't make sense, and then you rerun again and found an error, and then you understand a little bit more of the things you were doing, and one day you do have results and they're interesting, and then you look at them and you think, how more interesting can I make this? And it's for these 2 days out of 100, or even sometimes even more, even like 300 days, that makes everything worth it, to be honest.
So we have a keen audience, and the question is, can you explain in simple words how you use Bayesian inference to determine the bounds on the masses of the neutrino?
This is someone that knows what they're talking about. So what we do here is that in this case, in this analysis, we have a bunch of likelihoods for each of the experiments and the data. And all these likelihoods are being analyzed together. So we have codes that generate the theory. The theory is compared with the data in this thing that we call the likelihood. But because we are Bayesians, because as I mentioned, we can only infer what the universe is made of because we only have one, we also need to put in there our priors. And this is, I think, in the jargon of science, and somehow controversial from some people, although I am, I think, a fierce Bayesian. But the way we do this is by using the mass of the lightest neutrino as our primary parameter. The bounds that we know from particle physics, so those measurements on the differences of the masses, we put as Gaussian priors, and we also sample those parameters. And we, from these, infer what the sum of the masses is, and it's the sum of the masses that goes into the theory and compare with the data that we have. And to be even a little bit more Bayesian, as I mentioned, we do have these two types of mass orderings of hierarchies. So we did this thing of also being agnostic about it and then just switching randomly between the two orderings. And then in the end of the day, because you're doing Bayesian statistics, you can do something that's called marginalizing over, which is a fancy name for ignoring it.
Thank you, Arthur. I think we will end up on this high. So you've seen the two extremes of how complicated it can go. Yes, thank you again for this great talk, Arthur.
Thank you for inviting me.
Cute talk as well, I have to say. I'm still not over this. So yes, so yeah, it's been a bit quiet tonight. So please don't forget to like and share this video. We actually get most of our view from people that join later. I mean, they don't join, they just rewatch. So yeah, share to all your friends if you think it's great. We also have other videos on the channel. And if you go to our channel, you'll see on the right, left-hand side, I never know, all the other astronomy on tap from everywhere in the world. So if you need more astronomy, there is always more, which is great because the universe is infinite. And so you have more astronomy. In 2 weeks, so in 2 weeks, we'll come back. We will have a break next week. And we will basically come back with completely the opposite of Arthur, which is we won't talk about theory and simulations and cosmology. We will talk about exoplanets and instrumentation on how we detect exoplanets. So the very two opposite bounds of astronomy and astrophysics. And we will have someone from Queen Mary. So again, we're continuing our tour of all the universities in London. So until then, please take care. Take care of you and yours. And don't forget to subscribe and follow us on Twitter and Facebook. And thank you, Arthur, again.
Bye.
Bye. Bye.
Yes, okay.